Okay, section 5.3 is about the fundamental theorem of calculus, which I will sometimes call the FTC. Here we have the graph of the function y equal x, which you can also write like this, and it's just a line through the origin. Okay, notice that the function is continuous on R, and of course it's also continuous on this closed interval. Continuity plays a big role in the fundamental theorem of calculus. I'm going to define a new function. It's gonna give me area. Okay, so the input of my function is the upper bound of integration in a definite integral. So that's my input. My output is going to be the definite integral from -1 to x of this nice function up here, the line. Okay, now the reason I'm using a different variable is mainly just to have good form. I've already used the x as my input, and so I'm going to use the variable t to represent the variable of integration. The differential dt here just is telling me which variable I'm integrating with respect to, and it's t. So this is my integrand, t, my function. So let's evaluate this function just so we know what it's actually giving us. So g of -1, okay, is just the integral from -1 to -1 of my function t, and that's just equal to 0. That's a property we have of definite integrals. G of 0 is the definite integral from -1 to 0, so there's my input. And now in order to compute this definite integral, I could use the limit of Riemann sums, but that would take a long time. And it's much easier just to look at the graph of the function and interpret this definite integral as area. So this is going to be the net area between my curve and the x-axis between x equal -1 and x equals 0. And I can calculate the area here as a triangle with area 1/2, and since it's below the x-axis, it contributes -1/2. So let's evaluate g of 1. So if my upper bound of integration is 1, then my output is the definite integral from -1 to 1. And since this function is odd, we can see that these two areas are symmetric, but one is negative and one is positive, so they will cancel each other, and we'll get that g of 1 is 0. And I'm also going to evaluate g of 2, and in this case we're just taking, finding the net area from -1 to 2. And if you add up these areas, you'll find that the area here is 3/2. Okay, in other words, I'm just adding this area to the 0 here. So here we have the statement of the fundamental theorem of calculus part 1. So I'm just going to read it. If f is continuous on the closed interval AB, then this new function, which we can call the area so far function, that's what I like to call it, is differentiable on the open interval AB, and the derivative of the area so far function is just f of x. Okay, so this is just saying that this function that we just talked about in the previous page has derivative equal to f of x, the integrand. Okay, another way to write this, so in other words, we could write this as d dx of the area so far function is equal to the integrand. Two main things that this is telling us. One is that g is an antiderivative of f. So the area so far function, this thing right here, is an antiderivative of f. So if we differentiate it, we get f. The second major thing this theorem is telling us is that if I start with the function f, and then I integrate, and then I differentiate, I get f back. So at least in one direction, it seems that integration and differentiation are inverse processes. Okay, but next I want to do some examples of how, what some of the homework problems will look like. So use the fundamental theorem of calculus part 1 to find the derivative. Well, this just tells us the derivative is the integrand, that's all. So in the first example, I have g of x is given by 2 to x, the definite integral from 2 to x. So this is a pretty standard. Here a is 2. And in the upper bound, I have my independent variable. That's important to look at these bounds and make sure they match what you see here. I have a number here and x here. This is my integrand, so that's the function, and I'm integrating with respect to t. Okay. Now, the derivative here is just the integrand. So g prime of x is just equal to square root of 5x cubed minus 7x, and you're done. That's the simplest case. So let's look at another example. In the second example, b, this function is almost exactly the same as the previous function. The only difference is I've switched the bounds of integration, so now the constant 2 is on top and the variable x is on the bottom. Okay, but everything else is the same function, same differential. Now, we know that there's a property of integrals that says if you switch the bounds of integration, then you will get the opposite value for your definite integral. So what I'm going to do first is I'm going to rewrite h of x as negative definite integral from 2 to x. And then I see that, well, taking the derivative, this is just a constant multiple, I just get the opposite of what I got in part A. Okay, so this is all there is to that. The third case I want you to take a look at is examples like this one, where now the only difference between C and A is that my upper bound here, my upper limit of integration, is actually a function, sine x. So in this case, we're going to have to see this as a composition of two functions, and then we will use the chain rule. Okay, we're going to do one more example. In this version, instead of having x here in my area so far function, I have another function, sine x. So this area so far function has the structure of a composition. So this has a structure of h of x is equal to, let's say, g of f of x, where my inside function f of x is sine x, and my outside function g of x, this function is an area so far function, and it's the same one we saw in part A. Okay, so we know that the derivative of f of x is cosine x. We also know that the derivative of the area so far function is this function right here, but I'm going to substitute f in here in anticipation of the chain rule, and that is going to give me 5 sine cubed x minus 7 sine x. Okay. So now, using the chain rule, we know the derivative of our composition, and this is going to be our final answer, is g prime of f of x times h prime of x by the chain rule. So this is equal to times the derivative here, cosine x. Okay, so this is the derivative of this area so far function, which as I said before, this is a composition. So this fundamental theorem of calculus has a second part. This is the fundamental theorem of calculus part 2. And what it says is that if f is continuous on AB, then the definite integral is equal to f of b minus f of a, where capital F is any antiderivative sorry, kind of ran out of space here, any antiderivative of f. So remember, antiderivative just means that the derivative of this function is this function. So I'm just going to do a couple examples to show you how this works. The first thing is I want you to remember that in section 5.3, if I wanted to compute the definite integral, then I had to use the limit of Riemann sums, and that was a lot of hard work. So what this is, or another option we had was to try to compute this as area, but this one will be pretty difficult to do that way because it's a curvy. It's not like a straight, it's not a straight line. So in this case, this would be very difficult for us to compute. But using the fundamental theorem of calculus, what this is saying is that if I can just find an antiderivative of this function, then all I have to do is plug 4 into that function, plug a into that function, which is 1 in this case, and subtract. So let me just show you what I mean by that. So first I'm going to rewrite this function. So f of x in this case is, let me write it as x to the 3 halves minus 3x over x to the 1 half. So this is x to the 2 halves, or just x minus 3x to the 1 half. So rewriting it gives me a simpler, it's easier to find an antiderivative when it's written this way. So an antiderivative of this function would be x squared over 2 minus, now I'm going to add 1 to the exponent, and then I'm going to divide by that same number. So this gives me 2x to the 3 halves, and I'm just going to double check. If I take the derivative of this, okay, I'm going to get an x here, and this will give me, yes, 3x to the 1 half. If I take the derivative of this term, I get this. Okay, so remember the first thing that we did was we rewrote this function like this. And then we found the antiderivative of this function, which is this function. Now the fundamental theorem of calculus is telling me that the antiderivative here is equal to, I'm going to put some intermediate notation in here. It's equal to the antiderivative evaluated at 4, and then subtract the antiderivative evaluated at 1. So this is a notation I can use to express that. And right here I'm going to start doing the evaluation. So I have 4 squared over 2 minus 2 times 4 to the 3 halves. And then I need to subtract 1 squared over 2 minus 2 times 1 to the 3 halves. Okay. Okay, so let's evaluate this. So I get 16 over 2, which is 8. 4 to the 3 halves, I take the square root of 4, and I get 2. And I cube it, and I get 8. 2 times 8 is 16. Here I have 1 half minus 2. So this is 8 minus 16 minus 1 half plus 2. And this to me looks like negative 6 and a half. Okay, so that is my net area, and that's the value of my definite integral, negative 6 and a half. So just to recap, we rewrote the function, we found an antiderivative, and then we evaluated the function at the antiderivative. So this is f of 4, and this over here is f of 1. We subtracted and we got these values. Okay. And that was much easier than using the limit of Riemann sums. So let's do one more example here. So I want to evaluate the definite integral of this function from pi over 6 to pi over 4. Instead of using the limit of Riemann sums, we're going to use the fundamental theorem of calculus part 2. I don't really need to rewrite this, but we need to find an antiderivative. Okay, if f of x is equal to 5 secant x tangent x, then I can see one antiderivative is just secant x, right? Which we know is, 5 over cosine x. Okay, so this is my antiderivative. That means that the definite integral is going to be 5 secant x. Okay, and what this means is we're going to take 5 times secant of pi over 4 minus 5 times secant of pi over 6. And this is just 5 times 1 over cosine of pi over 4 minus 5 times 1 over cosine of pi over 6. So that's cosine of pi over 4 is root 2 over 2. So this is going to be 10 over root 2. Cosine of pi over 6 is root 3 over 2. So this is going to be 10 over root 3. And then if you want, you can, write this as one fraction, simplify a little, factor. Okay. Etc. Okay. So again, just to recap, in order to evaluate the definite integral without using the techniques from section 5.3, I just found an antiderivative, which was this function, and I just evaluated my function at the upper bound of integration, the antiderivative, and the antiderivative of the lower bound, and subtracted.